Okay, hi everyone. Welcome to FOXXCON September. All right. So first of all, just a show of hands, how many of you guys are pursuing or have pursued core computer science, as in BTech in computer science or something like that? Pursuing or pursued. All right. I asked this so that I know, exactly in how much depth to explain things, right? So it looks like we have a computer science crowd. That's nice. So let's start with the topic of discussion, that's weaponizing havoc for evasion. Before that, a quick intro. I am Siddharth Johri, also known by my online alias JoDescribe. I am a security consultant at Redfox Security, and I'm very happy to see such a nice turnout over here. Mumbai Rain's doing the best that they do, and yet everybody is here for cybersecurity. So this talk is and demonstration is going to be about the C2 framework Havoc and how we can modify it to uh, cater it towards defense evasion. Right? People who are not uh, familiar with Havoc, have you guys used Metasploit? Yes. Right? So you can boil Havoc down to a very advanced version of how the meter works, right? Let's just say, right? So have Metasploit has a lot of modules to attack software and CVEs, right? Havoc does not have that, but all the features that Meterpreter has, more or less, are present in Havoc, and there are some extra features as well, right? So you can assume Havoc to be something like Meterpreter, right? Like a framework which has something like a Meterpreter. So we'll start with Havoc, and then we also have some more cool stuff coming, which is against geared towards defense evasion, right? So Havoc, it's a modern C2 framework. It's not built like Metasploit, right? Metasploit is more geared towards initial access, right? It has post exploitation modules, very amazing modules, but it's more geared towards initial access. Havoc, however, is more geared towards post-exploitation activities like pivoting and deploying beacon object files, or rather executing beacon object files stealthily and while evading defenses, right? So this is how usually we generate a payload inside of Havoc, right? And this is one of my favorite configurations to have, having indirect syscall, stack duplication, and echo sleep technique turned on. So you can take a screenshot of this if you're not, or like a photo, if you're not familiar with those terms, right? You can go home, look these up. uh, these are not pertinent to the demonstration, but these are some very interesting techniques that Havoc uses to evade defenses itself, right? All right. So let's actually go ahead and generate a payload. Right, so the IP that we have over here is 1.8. So we'll deploy a listener based on that same IP. Let's call this FOXXCON demo. Okay, so what this will do is it will basically open a port up at port 80. So let's actually change that. Let's not keep it 80, right? Let's keep it something weird, because why not? Right? So it will open up this port and it will listen on this port for incoming connections. Now, Havoc is very nice in terms of how modular you can make it and how different you can make the network traffic going in and out. So here you can see that there are fields for headers and URIs. For the sake of the demonstration, we don't really need to edit them or actually do something with them. But if you see this pre-configured listener, you'll see that it has some headers and some URIs which make it seem like it's a Microsoft Teams network packet on the application level, right? So essentially, when a network or a NOC analyst, right, looks at the traffic, then they would even if they have SSL offloading and they take a look at the HTTP packets, they might assume that this is for Microsoft Teams, right? And this is not really something malicious. Either way, so we have this new listener over here, and let's create a Windows executable which is supposed to give us something like a reverse shell or a meetup header connection, right? I'll talk in terms of meetup header connection because I guess you guys are more familiar with Metasploit, right? But it's not a meetup header. However, it's something very similar to that, right? By the time that compiles, what we are going to do with that payload is we'll turn off Windows Defender and the cloud integration, and then we'll use a tool, an open source tool called threat check, to see exactly what bytes of the payload is irritating Defender, right? So Defender does not look at a binary and says ki mujhe, I don't like the whole of it, right? Defender goes through the binary and there is usually a certain part of it that Defender does not like. It could be a sequence of bytes. It's usually a sequence of bytes, or it could be just an ASCII string, right? So what we're going to try and do is narrow down exactly what string it is, what set of bytes it is, and then remove those bytes somehow without breaking our payload. So what threat check does is, okay, first off, I hope everybody is familiar with binary search, right? So what threat check does is, let's say this is our malicious.exe, right? So Defender has labeled this as malicious. So threat check will break that into two equal parts, right? And two equal parts as in by bytes. So if it is, it's a 10 KB file, those two parts will be 5 KB and 5 KB. And then threat check will ask Defender to tell us which one of those is malicious. Now note that both of them can be malicious, right? But this is just a demonstration when there is only one set of bytes which is malicious. So again, Defender picks one, says this one is malicious. Threat check again breaks that into two parts, and eventually we get a sequence of about 64 bytes. I think they like the tool has increased the number of bytes which it presents. That these bytes are what Defender does not like, right, out of the whole file. In case of multiple occurrences of bytes or byte sequences which Defender doesn't like, threat check gives us one at a time, right? So threat check is like, first fix this, then we'll talk, right? So let's take our payload and put that through threat check. Now this is Windows 11. So if you guys have Windows 11 and you do any sort of malware development, or if you have ever tried to use your Windows, just as a step to transfer Metasploit payloads, you would know that Windows 11 is very intrusive, and even if you set up exclusions and no matter what you do, Windows Defender somehow manages to overrule you and delete all your malware. So we might have to do this yet again. Right? Just if at any moment something is not visible or legible, please let me know, all right? Okay, I think we did not copy that. Right, so we'll use thread check and we'll ask it to assess this payload that we have just created. Now thread check is pretty quick with it and it gives us these so many bytes, right? And what it says is that identify the end of bad bytes at a particular offset. So thread check is telling us that in this particular binary, your first obstacle is at this address space, like it ends at this address space. So anything before this particular offset, right, a certain part of it is malicious, or it is something that defender considers malicious. So now what we can do is we can reverse engineer, or rather decompile the binary and try to figure out what exactly in the Havoc agent's source code it is that's triggering this, because as per thread check it's just bytes, but it's not bytes in the end, right? It's some compiled code, right? And those bytes depict a part of that compiled code. Now that compiled code comes from source code, right? So if we change compiled code, then we might end up breaking some functionality, right? Let's say if the compiled code is representing x is equal to x plus 1, right? And that is what is getting detected. Let's say we change that signature to make it seem like x is equal to x plus 2. So we changed the signature, but we broke a functionality, because now the code was dependent on the statement being x is equal to x plus 1. Whoever wrote the code wrote it assuming that this particular line will have the expression x is equal to x plus 1. But now we made it x is equal to x plus 2. So that's not fine. That's not cool. Now it won't work, right? So let's see how we can actually change it without breaking it. It's not breaking. Okay, I had not imported, my bad. Okay, so the file offset was 7E9, right? And I think the text is too small to read, even though I scaled things up, but this says file and in brackets, the offset. Right? So here is exactly where the malicious code lies. If we go back to thread check and we see these bytes, it starts from D0, FF, C0 and ends at E9, A1. Sorry, 1A, right? So let's go to git draw and we can see exactly these bytes, D0, FF, C0 and till E9, 1A, right? And when I select those, this whole block gets selected. Now if I go here and see what exactly the decompiled portion of it is, then I come across this line of these 5 lines, right? And now the thought behind this is that if we change something here, right, naturally something will change in the decompiled version. But since we don't have extra space over here, right, we cannot do a next line in the assembly. But what we can do is we can go back to the source code, find where these particular 4 lines are, add some extra instructions over here so that when that compiles, this particular block does not look the same, right? Now, if you are wondering why did I only pick the last line from the thread check, right? Because that's what I did, right? I only talked about this line, right? I did not talk about this. So I talked only about this because this says end of bad bytes. So now I don't know how long these bad bytes are, but what I know is that they end over here. That means few out of these bytes are definitely bad, right? So it makes sense to change this particular, this set of hex bytes. It may be so that bad bytes start from here and end till here, right? But if I change something from here, then the whole signature will change. And maybe the next time thread check tells us that, okay, you cleared this, these are still bad bytes, right? That could still be possible. So thread check basically asks us to go one step at a time. So let's actually try to understand how to find this in the source code, right? Because this is just some random C code. How would we even find this in Havoc's source code? So first, let's take some pointers. This is inside of a while loop, right? One big while loop. And this parameter 2 is getting incremented right before the loop ends, right? So we can definitely rewrite this as a for loop, right? Because there's an incrementation. So instead of using this particular variable, we can use I, right? So in this particular statement, we have one iterator and we have 2 variables, right? That's all we have. And we have this particular symbol which represents XOR, right? Moreover, if we go a little up, we see that there is another loop over here, another do while, right? And just like every do while and for loop, this can also be rewritten as a for loop, however so, right? If we go a little bit up, we also see that there are a few functions executed before we come to this line, right? So let's just keep these particular pointers in mind, that there are 2 functions executing before this. There is a loop before this, and whatever line this is, it's right before the loop ends, right? And this has one iterator, 2 variables, and a XOR sign, okay? Now, it's a lot of information, but to understand what exact part of the source code we have to target, we have to keep all of these things in mind. So let's go to the source code. Now, since Havoc is open source, as soon as you clone Havoc, you will naturally get all these files. And once you compile Havoc, before running it, before actually deploying it, you will have to compile these, right? So you will have them as a source. So I have opened the source for the agent, which is called the daemon in Havoc terms, right? In Metasploit terms, it would be the meetup, right? So this is basically the source code for Havoc's personal meetup, kind of. So let's try to search. Now, if we're only talking about regex or semantics, out of all the things that I said that we have to take care of, what is one thing you can search for in this particular field so that you can, maybe get a broad idea of what all lines of code you have to see, right? I'll show this to you again. The actual decompilation. Yeah. So these particular 4-5 lines. What part of this do you think is something you can search for, or you can write in Control F, and you'll probably have this line of code somewhere in the thousands or maybe tens of lines of code, right? XOR sign. Perfect. So let's do that. Right? Let's search for the caret sign. It's actually called the caret, but yeah, it does the XOR. So the first iteration of this is a printf statement that doesn't really help us. The second iteration is again, it's a comment, doesn't help us. Now, all of the remaining iterations, or rather all of the other occurrences are inside of this AES script block or file. So now we can gather a few things from here. First one, whoever configured Windows Defender to treat those particular bytes as bad bytes is very smart, because if we change any of those bytes manually, then we'll break the encryption, right? So if you're encrypting things, they won't get encrypted properly. Or if you're receiving encrypted things, we won't be able to decrypt them properly. So hence, our whole communication will be broken, right? And the whole concept of command and control is based on communication, right? So first thing is that. Next, we can move on to each iteration one by one and see what's up. So first, we have this iteration. It's inside of a for loop. That's great. There's a for loop right above it. That's also nice. But there are no two functions executing above it, right? And moreover, it's not at the very end of the loop. So let's move on to the next. These ones are at the end of the loop, but you would see that these are 4, first of all, right? We do not have 4 instructions there. Even if we assume that some sort of compiler optimization got rid of it, it's still a part of the same function, right? So it has no 2 functions above it, right? Now let's get to the next occurrence. Now this can't be it, because it's part of 2 for loops, and there's not a for loop before it, right? Let's move on to the next. This one does not have a loop at all. And we can rule all of these occurrences out, because there is not a for loop above it, right? Or a while loop. Okay. Right. So now we have this particular line. It's a part of a for loop, right? It has a for loop before it. There are 2 functions being executed somewhere before it. And this function, it has this instruction has one iterator, one variable that's buff, and buffer bi, the second variable. Now, if you feel that this is a variable and this is an iterator, then you would have to read this block of code, where you would find out that bi's value has been finalized. So bi is not an iterator, hence buffer brackets bi becomes one entity, right? Hence it's a singular variable in optimized code. So this is actually satisfying all of the conditions, right? So let's change this a little bit. Now, if we look at how these are defined, how buffer and buff are defined, they are defined using, they are an array of uint 8s. So let's create a new variable. Is anybody here whose favorite subject has been finite automata or compiler construction? No? Okay then. Now what should I put in here so that in the end this is the thing that happens, but it's not exactly the same. Like I've just written it in parts. What should I write here? Yes, yes, come on, quick. What should I write here? A's or B, right? So now these three lines are essentially the equivalent of this one, right? So we have changed the source code a bit. Now let's recompile it and see what really happens, right? Because our agenda is to get rid of those bytes. So let's go back to Havoc. Let's create the payload again in the exact same way. Did somebody ask a question? Yes, the logic was exactly the same. I just broke one line of code into three, right? I wrote bad code so that the signatures change. That's all I did. Right, you can take a look at it again. I left the original instruction in comments, right? So it's essentially the same, right? If it's not the same, it will break. So let me confirm. Yeah, it's the same. Right. So while that compiles, a quick recap of what we've done till now, right? Just so that we are on the same track. We used thread check. We figured out what the bad bytes were, right? I searched based on offset. While showing you, you can also search by bad bytes. It's Ghidra, they have features. Then we figured out what block of code it is that represents those bad bytes. We tried to find them. We will know if we found them or not in the daemon source code. And we modified this piece of code just a little bit so that it is a teeny tiny bit different, right? Now let's see what actually happens when we put this through thread check again. So we can just delete it from here, doesn't matter. Right, so that file is gone. Let's shift the daemon back into downloads, right? And now let's do this again, okay? Let's put the file, the new created binary, through thread check again. And somehow it's still a malicious file. It's still not a benign file. And somehow we have the exact same set of bytes as before, right? So we have got to be doing something wrong, right? So let's open this up again. And let's see what has changed. Because something has to have changed. We changed the source code. So something has definitely got to be different. 。  . 。  . 。 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . .
。 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 . 。 。 。 。 . . 。 . . . . . . . . 。 。 。 。 . . 。 。 . . . . . . . 。 。 。 。 . . 。 。 . . . . . . . 。 。 。 。 . . 。 。 . . . . . . 。 。 。 。 . . 。 。 . . . . . 。 。 。 。 。 . . 。 . . . . 。 。
So let's again go to this particular offset. And what we can see is this is exactly the same. This has not changed one bit. And if you were to compare this to the other binary, you would find everything above it is exactly the same as well. It's nothing different, it's exactly the same. And that is troubling for us because this was one way we were going to avoid. We were going to avoid being detected by Windows Defender. This is the reason why this happens, right? There is absolutely no change in the compiled bytes. Changing a few lines in your code, for example, instead of x is equal to 2, which was the optimal code, I broke that down into 2 and I saved it as a source code. But the compiler does not take that line down. The compiler wants optimized code, no matter what. So the compiler folds that in the intermediate representation stage. It gets rid of everything that's that can be determined at compile time. For example, if you take this small piece of code, it can be folded twice into returning 2, simple, right? We can complicate it, like you can write bad code, but the compiler will convert it into as decent of code as possible, right? That has what has happened with us. Now, just to give you a small, a small insight into what all a compiler can optimize away, I made a table, right? I took some help from ChatGPT as well. So basically, you have front-end simplification, which we did, right? We wrote x is equal to 4 as x is equal to 2 plus 2, speaking in broad terms, right? We broke that one perfectly fine line of code into 3. There was no need to do that, and compiler actually collapses that code into the same set of bytes, right? And then there are these all different ways you can do that. You want to take a picture, you can take a picture, get to it later. It's not really pertinent to the subject though. To boil all of this down, okay, you were taking a picture? Sure. Right? To boil all of this down, your typical harmless edits that will get optimized away are reformatting, commenting. I hope everybody knows comments don't make it past the compiler, right? So if you add comments, that will not change the signature. Renaming your symbols like variables, that's going to do absolutely nothing, right? It will not change signatures. It does not change the abstract syntax tree. Can I see some trauma, some people who have learned about the abstract syntax tree? Anybody here who loves the abstract syntax tree? Have you guys studied about it? And okay, we have a mix of yes and no. So there are some people who have not been through this, then that's nice. If you add statements like if def and something like that, these get stripped away at compile time as well, right? The compiler decides if it wants to compile a particular sequence of or a particular set of lines of code at compile time based on this, right? So it's more of a developer's utility. It does not make it past the compiler. And if you introduce a variable that's never read after the last line, for example, instead of breaking it into 3 lines, I could have made a new variable which was an arithmetic manipulation of the other variables used. But if I was not going to use it later in code, the compiler will actually drop that line of code in the intermediary representation stage, right? It will not make it to machine code. That variable will not exist in machine code if it's useless. And naturally, arithmetic simplification will and algebraic simplification will also be removed. It will not make it pass. Now, the question is, how do we beat it? Now, the compiler can play a part of an adversary if we are looking at it this way. Later in the demonstration, you'll see how the compiler will become an ally, right? So this is what I was led to when I was searching about ways to get past optimization. So this is a particular keyword called volatile used mainly in hardware programming, right? So now we're using a utility designed for people who make firmware, etc. And we're using that to modify our malware, right? That is exactly the kind of research that goes on, right? This was a very small Google away, right? But sometimes it takes a lot of while. So basically what this keyword does is it tells the compiler that this particular variable might get affected by the hardware, right? Maybe this variable is reading the value from a hardware register. So do not make this a part of your software optimization, right? A few stages of your software optimization need to be skipped on this particular variable. So let's go. Let's try to use this. We can go to these same lines of code, and all we have to do differently is use the volatile keyword. Now this is only one of the ways to get rid of this particular signature. You can definitely make this a very complex expression, and maybe the compiler lets that go through. However, this is one of the cheeky ways that you can just get past a few stages of the optimization cycles. So let's save this and compile that again. Right, okay, it did get saved. Let's compile this again. So you pick our listener, select all of the amazing features that Havoc naturally comes with, and generate. Right? Now again, it will take a small while. So till then, let's make other things ready. Let's get rid of this. Let's also remove this again. Don't need that. Okay, so now for this I'll open a new tab because I have a gut feeling that we've just gone through Windows Defender, or maybe because I've done this before. So now you can also use this to you can use the AMSI engine for people who are curious to scan PowerShell scripts just in case, and it does the exact same thing for scripts. The only difference is to debug it on script level is much more easier because it gives you literally the clear text that you have to change. For us, the engine is Defender that gets selected by default. Okay. Okay, so let's put this through threat check. And this time threat check says no threat found. So this means that if I turn on real-time protection right now and try to execute this, or rather copy this file to my desktop, Windows Defender will not say anything. Windows Defender will be cool, right? So let's try and do that, because is anybody asking? Yeah, sure.
If वो जो original single line code था, उसमें अगर volatile syntax अगर add कर दिया
see, so why naturally you have like tens of thousands of ways to change that signature, but if you But if you put volatile over here, you're telling me volatile. Okay, that would not work because this function, this particular array has already been defined over here. As in, it's just a pointer to an array. So you can't change the type of the variable in middle of the code, right? It would have to be volatile PU8 DUF there, and not just here, but wherever it is being passed to this function. Right, so that all is the coding part of it, right? You want to get into coding, there are hundreds and thousands of ways in which you can perform this simple function. You can make a new function which just returns those values, and it will be registered as a function call. Or maybe it doesn't because the compiler inlines that, because the compiler is also notorious to doing that. If your function is simple enough, the compiler will not make a function call, it will copy your whole function there, right? So you have to be careful, and it's just up to a little bit of trial and error that you have to change the source code, right?
So I have a question, sir.
Yeah.
So what about instead of using that XOR operation, can
Yeah.
we create our own XOR function? And whatever operation that XOR does,
Yeah.
we just simplify it plus minus or whatever arithmetic operation that we have. That will change the
See,
XOR string.
it has to be symmetric, because to me, only looking at this particular function, it feels like that this function is going to be reused during encryption and decryption, because XOR is a symmetric cipher, right? So if you have to create a function, then it has to be a symmetric encryption function. So it doesn't not even have to be XOR, right? There's a chance that it could be something different. However, it also says AES. So this may just be a function that is part of a much larger routine, which actually puts through the communication through the AES encryption.
No, my question is not related to that AES function.
Yeah.
Particularly to that
Just the XOR function.
That XOR.
Yeah, so that new function that you create has to be complex enough that the compiler doesn't say that we can just yeah, because then it will just copy the function over here and inline it. So we don't have any threats there. So let's see what has changed, right? Because something has to have changed if defender has not identified this as malicious, then those bytes have got to be changed. So let's see what kind of a difference that has made. Let's go to that same particular offset, and now we see that the code is a little bit different, right? Just a little bit different on this end, right? The bytes are different. They don't look the same. They feel a little more voluminous. So let's select this particular block, right? So these 5 lines, if you compare to what it looked like before, and I'll show you. Yeah, so this is what the original function looked like, right? This is what it looks like now. If you notice, nothing much has changed. Only the name of this variable has changed, right? And that shouldn't be, a part of the signature, right? I just said that renaming symbols doesn't really do anything. So what is really different here? So if you take a look at the bytes, the bad bytes, they started from D0, FF, C0, right? Down till here. But the ending has changed. So the end is not the same. If I select all these lines of code that are supposed to be changed, somehow these 4 assembly instructions are not a part of it, right? These 4 assembly instructions are just there. They're not really a part of the compiled code. So what are these instructions? These instructions are basically telling the compiler to get fresh copies of the variables that we just declared, right? We declared A, we declared B, right? So every time we gave them a value, the compiler was, the binary was told, the compiler told the binary to immediately write it into memory, right? And when we were fetching it to assign the value to buff I, it was told to read those registers again in case they have changed. So it's not a part of the software, right? But it's not really a part of the hardware either. But it's you can say it's something that the compiler tells the binary to do. That if you're going to use this particular variable, fetch the value again in case the hardware has flipped the register or something like that, right? Hence, the signature has changed, but the function remains the same, right? Okay, so we got through that. Now let's see, does this still work, right? Because there's a chance that this doesn't work. So let's copy it. Okay, first let's turn on real-time protection, and let's copy this daemon to our desktop. Right. Now, if this is a malicious file, what would happen if I copy it? It would get instantly nuked, right? Let's see if that happens. It can still happen. It's very uncertain. Okay. So Windows Defender is not really, throwing up alarms. So let's see if we can execute it. Let's check back, and we have a session here, right? Now this is, again, if you click on this is something that you guys might find to be a little bit more familiar. Like this is the command line kind of, right? Assume, right? And if you write something like help, this is exactly the way Metapredator, also tells you how its functions work, etc. And it's in general how all other C2s work. Now, we may have broken some sort of functionality, right? So actually we would not have, because the code is the same, but just to be on the safe side, let's run the whoami beacon object file and see if we can actually get things running. Yes, we're getting things running, right? So we have Windows Defender, we have real-time protection, and just by changing a few lines of code in one of the most popular C2 frameworks on GitHub at the moment, we were able to get past Windows Defender. Now, we have now got to make this even more robust, right? We have to target cloud-delivered protection as well. So let's take a look at some more interesting things. One of which is actually somewhere here. Okay. So some Yara rules. Now, are you guys familiar with Yara? What is Yara? Okay. So let's start from what is Yara. So Yara is essentially a pattern matching tool, right? What it does is it defines strings or byte sequences and defines a condition that if this condition meets, then the particular sample that you have given to me is of the type Havoc and whatever code is given to it, right? So I have picked out all the rules from Elastic Security's GitHub repository, in which they have created a lot of rules to detect Havoc, right? Or Havoc agents, or demons as they're called. So one simple description of how this would work is, I'll zoom it a bit, right? So everything above the strings portion is just metadata, and you can safely not pay attention to it much, at least. So it has defined a few strings. The first one is core, and it's this particular byte sequence. The question marks can be any byte, right? So what this particular variable or what core says is that if in the whole binary you find any set of bytes which fall into this pattern, right? Which have 48, then 2 random bytes, then 2C, 06, 000000, then 2 bytes, and so on, then core is true, right? The only core is true. Then there's the same for command table, and then a lot of definitions of hashes as well. And then it has defined a condition that if either core is there or command table and all of hashes, like this I think is very close to normal English, right? You can read this and you can totally understand what the condition means, right? So if this condition is true, then the Yara engine or the binary Yara binary will tell us that whatever you have supplied to me is of the type this Windows Trojan Havoc 77FE whatever, right? So there are a lot of rules that Elastic has written for Yara, right? I have gotten all of them and put them into a single file. Now this is only one set of Yara rules that Elastic Security has put on their GitHub. Malware researchers across the world, right? They make their own Yara rules for different things, right? And they may or may not make that public, right? There are a lot of private threat intel feeds which would have Yara rules from a particular company, which sources Yara rules from them. So your best bet at not letting your malware be detected is to gather as many Yara rules as possible available in the public domain and make sure none of them detects it, right? So that is one good way. It's not foolproof naturally because you've not gone through the ones that are private, but you can't, right? So let's focus on some things that we can actually fix, right? So for demonstration purposes, I've only picked the Yara rules from Elastic's repository. So there are a total of 4 rules. And now let's put the daemon through those 4 particular rules. I think this is the syntax. Okay, so now Yara has given us an output that this binary that you have given, okay, so the Yara syntax is Yara binary, then the rules, then whatever binary you want to analyze. So once I did that, Yara told us that this particular binary can be identified as a type of Windows Trojan Havoc, this particular thing, okay? So even though we got rid of, a particular signature that Windows Defender was detecting, Yara, one particular Yara rule can still look at our binary and say that this is Havoc, right? So now let's get rid of that. So for that, we'll have to open up, it's FFECC. Okay, it's right at the end, right? So this is the particular rule that is being triggered by Yara. So all we have to do is make this condition false, right? The condition says commands tables and 4 of hash star, right? I think that can also be understood pretty easily that we need command table to be there and we need 4 out of any one of these to be present. Now this is a much bigger surface to target, right? It's much more difficult to target 4 out of all these because then we would have to get rid of say 5, 6 or 7 of these or 8 of these. It's much easier to target commands table, right? So let's see what this byte sequence decompiles to, right? Because just as we change some code for the bytes that Defender was detecting, we can change some code for the bytes that Yara is detecting. So we actually have this open already. So we can just take a look at these bytes. Okay, and if you're confused about what this 8 represent, it is the equivalent of 8 question mark question mark. So any random 8 bytes. So let's try to find if there is this particular byte sequence is there. There may be multiple iterations or occurrences of the same, but there is only one, right? And when we navigate to it, we can see the preceding ones also being present, right? We have 0B and then some zeros, and then there are 8 random bytes, and then there is 64, then a few zeros, and then 8 random bytes, which is exactly what is present here, right? So we've hit dead on that this is the particular set of bytes that we have to change. Now notice that when I highlight these, nothing really gets highlighted in the decompile section. Nothing is released there. If you scroll a little bit over there, you see that this is stored in the .data section of the binary, which usually houses variables. So this is essentially a variable and not a functional piece of code. So this could also be utterly, this could utterly throw the binary into existential crisis if we change it. This could, but it might not, right? So let's take that path this time, right? Last time we changed some code. Last time I told you guys that we can't just willy-nilly change a byte because that might break functionality. But this is not a part of the functionality. It's a part of the variables, right? It may be a part of some very essential variables, but this is something also we can try, right? So let's try. We can look at the bytes. This is the exact representation of the same. 0B, lot of zeros, 8 random bytes. So let's change this 1 byte here. That's all I'm going to change. Because if I change a lot, that would definitely break some functionality. So let's change the minimal possible number of things. And let's export this as an original file. Right, and let's call this daemon2.exe. Right, so I have saved it as daemon2.exe. Now what does daemon2 have? Daemon2 has the changed signatures, right? And it has 1 byte that I have changed manually, right? Rest of it is just compiled Havoc code. So we've got that ready. So let's use Yara this time for daemon2.exe. Okay, sorry, it was in Z. Now we get no response because as we aimed to do, that particular condition of the Yara rule is no longer true, because now instead of these bytes existing 6400000000000000, now we have a 01 at the very end. So this is not true, and hence the whole condition becomes false, right? So now Elastic's Yara rules cannot detect us. Windows Defender is anyways not detecting us. Let's see if the black box approach, right, of letting cloud delivered protection monitor us catches us or not. Because we don't know if cloud delivered protection will catch us until and unless we throw our malware sample at it, right? In Yara rules, we can still predict right? We can try to read these bytes ourselves without throwing it in the Yara engine. But with cloud delivered protection, we really can't, right? So let's try and do that. Let's delete this particular, okay, it's still running. Let's get rid of all these, this particular session. Let's delete this. Let's turn on cloud delivered protection. Now this is essentially the maximum protection that Windows Defender can give to your home laptop. Now let's copy daemon 2 to the desktop. Okay. Okay. So this is something that I can't really get past, right? If you do this on a fresh laptop, this might not show up, right? But this VM, I've done this numerous times. So Defender has gotten a little wary, but I will not definitely send that file for review, because why should I, right? So let's let that file exist and just wait for 5 more seconds to see if Windows has decided to nuke it, or if Windows is just not doesn't care about it. So I guess we can actually go ahead and execute it. First, let's see if Havoc is ready. Okay, Havoc is ready. Let's execute this. Now Windows Defender with cloud delivered protection may kill the process after it has executed as well. It's not necessary that if static detection has passed, that dynamic detection will also pass, right? But in this case, let's see what the case is. So we have a new session. It's healthy. It's calling back every 3 seconds. And let's again check the functionality, because we messed around with the command table this time. So there is a very good chance that we broke something, right? And initially when I was preparing all this stuff, right, I tried to do or actually touch most of the functionality of Havoc that I could replicate in a lab, but I did not find any one thing that was broken. Who am I was still running, and again, cloud delivered protection can kill this. That is still something that stays in the hands of Microsoft. So who am I works. Let's see if UAC bypass works, because that is no small feat, right? UAC bypass is a big deal. So let's see. Right, should work. And we have a new session, and it's not just any other session, it's a system session. So now not only do we have domain access if this particular user was part of a domain, we also have system level access to this machine, right? And Windows Defender is still up and running. Now there are definitely some things that if you run, then the Defender might definitely latch onto your process. But for initial access purposes, you've got initial access, right? Now you can go crazy. You can make your own beacon object files and run them. You can use other people's beacon object files and do whatever you want, right? So a small recap again of all the things that we did was that we first identified which rule Yara was detecting. We went back to see what bytes it is that we can change to make Yara not detect us. We changed a singular byte. We ensured that Yara is still not detecting us, and we ran it with cloud delivered protection, and not just the initial access, but also the UAC bypass, right? However, if you put the same sample on Elastic on a device having having the elastic EDR, elastic doesn't let it pass even the static detection, right? You put that device and it's burned, right? You can't even rename it. It's gone that quick, right? So now that makes me think that we had picked the Yara samples from Elastic's repository only, right? So there must be a set of Yara rules that they're keeping private. And hence, we can't truly rely on all the public Yara rules that we get, especially in cases of such extensive defensive solutions. So there are still ways to beat it, one of which is custom loaders, right? Instead of making Havoc write their default daemon, what you can do is you can take the shell code which they make. For example, in Metasploit, when you create a payload using MSF Venom, right? You have to give it a format, right? So sometimes you give a .exe, right? You need a Windows binary. Sometimes maybe you're targeting Linux devices. And in the same way, there is also one format, it's shell code. It's raw, position independent shell code. So we can do the same with Havoc, right? And we can inject it ourselves. The problem with custom loaders, again, becomes that they would still get caught because you might not be the best malware author out there, right? And because you're trying to write good code that you and your company and people on GitHub can understand, that means control flow will be predictable, right? If somebody decompiles it, they'll be able to understand what exactly it is that your loader was doing, and that's not something we want. And the optimizations that happen, right, they boil your code down to a certain byte sequences, which when decompiled will look pretty signatured, right? For example, if somebody does a code review on the decompiled code, they might understand directly that you're trying to do some process injection, right? So that's where we have something called as OLLVM. So it's the full form is obfuscator LLVM. Now this time the compiler is going to help us. Last time compiler was something that was coming in our way. This time the compiler is the one that is going to help us. So it is a de-optimizer. Instead of optimizing the code that you've written and boiling it down, what it does is it makes it even more ugly. I don't mean that it was ugly in the beginning, but just saying. So it makes it very ugly. If you, I'll actually show you examples of this later, but it makes the control flow very unpredictable. You can't look at the graph and tell what is going to happen next. If you put this through a debugger, that debugger is going to go crazy because it is going to have so many jump statements that you won't be able to keep track of what function you're inside. And the main purpose of it is that manual reversing becomes almost impossible. Now, there are definitely some amazing people out there who can take this piece of garbage that I give them and they can still figure out that it's not garbage, it's actually malicious. But when I show you examples, you would not probably compare yourself to those people, right? Because I don't. So the features that OLLVM has and what it actually does is, instead of removing algebraic simplifications, it adds, right? It substitutes the simple instructions with much more complex ones. You can see an example of A is equal to B plus C being replaced by these particular examples, right? It will create a random variable and then perform this sequence of things, which will eventually make it A is equal to B plus C. And what happens is then this particular byte sequence signature gets lost, right? And that is the first thing that was getting us, mixed up with the Windows Defender in the first place. So this is good. Then there is something called bogus control flow. If you have ever decompiled a binary, you would know that there's a control flow graph, right? So it basically, and from the time when you guys learned about compilers, there are basic blocks, right? And essentially, if you've written a very simple non-branching code with no conditionals and all of that, it would be in a straight linear format, right? If there are conditionals, it would branch out. So what this does is, the bogus control flow, it manually breaks your simple linear code into multiple parts and adds conditionals by itself and makes the graph look like a web. Instead of a linear rope or something of the sort, it makes it look like a web. And control flow flattening converts every conditional into a infinite loop, right? So if you know how infinite loops look like in assembly, then you're going to come across that basic block and you're going to think that this is an infinite loop. But somewhere inside of that infinite loop is a conditional that will break it out of the forever loop, right? So that was the instruction substitution. This is an example of control flow flattening. This is the same code. The output is going to be the same of this function. However, this is bad code, right? If you had to do something like this, then you would write this. You would not write this. So you write good code because you're good programmers, and you let the compiler make it ugly, right? So this time the compiler is going to help us. So let's take a look this time again, and for that we won't need the virtual machines. Yes. So I have prepared two Visual Studio solutions, and they are pretty much very elementary. So one is Hello World and the other one is Hello World OLLVM, signifying that OLLVM is being used to compile it. Now if you look at it side by side, can you even see the main code? Okay. So this is hello world.c, right? The first program that we all have written. Not even a space is different between these two. They are exactly the same, and this is the only C file there is. There is nothing else, right? But if I look at the project properties of both, then you would see that the Hello World the Hello World solution is being compiled by Visual Studio 2022 V143, which is basically the MSVC compiler, and our OLLVM version is being compiled by a toolset called LLVM. Now the toolset is LLVM, right? The genuine one, but the Clang binary that I have given it here is the one picked up from OLLVM, right? So this is basically using OLLVM. Moreover, in the command line instructions, I have given it a lot of extra variables, right? First of all, I've used bogus control flow. There are some more variables associated with bogus control flow, as in the probability and how many times I want this de-optimization to be run. So OLLVM does not only de-optimize it once, it de-optimizes it as many times as you want. For example, the compiler optimizes things hundreds of times. It gets faster every time because the things are getting smaller and smaller. Here it will get slower every time because it's bloating the binary every time it's going through the code. So we have instruction substitution, we have flattening, and then we have a AES seed, which will basically generate some more randomness into the code. It will basically create the seed for all the randomness that has to go into the code, right? So that's pretty much it for the properties. Now let's compile both of these, right? For that we'll have to clean the solutions first. and then let's build them, right? So let's build these solutions. And as you can see, the normal one got built in about 0.7 seconds, and the other one is still building. So let's take a look at hello world. Let's take a look at the hello world binary. Okay, this is fine. Right. So now this is the entry point. This is basically the binary creating the environment for execution. Now I don't want you guys to pay a lot of attention to the actual assembly code. Just remember what kind of shape and size this has. Okay, I'll run over it once or twice. Just remember what kind of shape it has, right? Right? Okay. So now remember that. And now here we have the main function somewhere over here. And this is the main function. This is how simple it is, right? And now I will attempt to describe what this actually does. This creates some stack space by moving the stack pointer. Then it moves the memory location of the string hello world to RCX. RCX is a particular register which is used by all functions as the first argument, right? So if there's a variable in RCX and a function is called, then that particular variable will be the first argument. So we have the first argument as hello world and the function getting called is printf. Now EAX holds whatever is returning or whatever value is returned by calling this function. And if you XOR EAX by EAX, you're essentially emptying the whole register, right? So you get rid of whatever value this function has returned because it's not being used. And then you reinstate the stack pointer to where it was. You empty out that space on the stack and then you finish the function, right? Even though you guys might not have studied a lot of assembly, was this pretty much understandable? Right? Okay, cool. That's nice to know. Now let's take a look at hello world ollvm.exe. Right, so this is again the entry point. You guys remember the shape of that particular entry point? It's pretty much the same, right? Pretty much the same. Okay. Yeah, but pretty much the same. Maybe a little bit longer, pretty much the same. Like I also not like read the code. Now let's go to the main function. Okay, so now I will not attempt to describe what's happening here. So you see these random, very absurd instructions, like they're doing AND between registers but not really using that value, right? They're using memory spaces, they're using hard-coded values, they're doing some stuff, but now I don't know which one of these registers they might use later. I have no clue. So let's go down, let's see, this is pretty long, and whoa, what is that? What is that?
Spider-Man.
So now this looks like a web. Now for people who have not done compiler construction and who might have missed it, these are basically basic blocks that I was talking about earlier. So that tall one was one basic block. These are individual basic blocks. And now we have a very interesting set of basic blocks and so many instructions everywhere and so many conditionals that we can't keep track of. And how many conditionals were there in my actual source code? None. It did not have one if-else statement. Yet, here we have something, right? Which is not really what I had written. And it just keeps going on. right? Now, let's say you have a lot of time on a Saturday, right? And you decide that I will sit down and I will figure out what this is doing, right? So then you might, I actually tried to do that. And all I could find was the hello world string somewhere here. Okay, right? If you remember from the previous basic block that I showed you, it also moved hello world to RCX and then called printf, right? But this time it's not calling printf, it's calling another function. So let's try to figure out what this function does, right? So now let's decompile this particular function that is processing the string hello world. Okay. It's also doing something. It just keeps going on. And I saw this and I said, ये तो नहीं होगा. Because you can't sit down and go through these basic blocks and try to figure out what's happening. And it's very difficult to even understand that printf is going to get called here, right? If you if you've tried to learn malware analysis, they would tell you that the initial stages are static detection, like static analysis, which involves decompiling the code and looking at all the API calls that are being done, right? For example, if you want to spot a process injection malware, then you would have the classic APIs of virtual protect and create thread and all of these things being called. But now with this, you don't know what is being called, right? And you can figure it out. You can definitely write some code to do that. I'm not saying that Python can't go through this, but it makes the task so much more difficult. And for a novice malware analyst, this is no mean feat. So now we have a very, very nice binary that we can, actually do something with. But it's just hello world, and making a custom loader is much more difficult. However, now after seeing this being turned into this and further into whatever that was, what do you think is the difference between their execution time? Because this naturally has so much more code to go through. How much longer do you think that this obfuscated version of Hello World will take? Give me a percentage, give me in seconds, any estimate. Any estimate, 5 seconds, 10 seconds. A normal Hello World gets executed in like instantly, right? How long is this going to take?
So whoever gives the right answer and maybe close, they will get a chance.
Whoever gives the closest answer. Yeah.
One by one.
16 seconds. Any other guesses? I'm asking how different, like how much different it's going to be, right? So, okay, so you said 16 seconds. 30 seconds? 5 minutes? 5 times. Anybody else? Any rough estimate?
Maybe a year.
10 times. 15 times.
1 minute, okay. So this is the original one, which takes about. This is the original one. This is the original one, right? It takes 16 milliseconds, 16.89. This is the OLLVM one. This is essentially the same time. So whatever it is doing in that assembly code is just, it's just distracting you, right? Because there definitely has to be some way that it can execute it. It's actually faster if you see. Right, it's somehow faster, right? If I run this multiple times, there are times in which it is the same amount, much slower, but the fact is the mean time is the same. right? So it's not that you're trading it off, right? It's not a trade-off that just because you've made your code so much more complex and ugly that it's going to take a lot of while to run or a lot of while to execute things. So if you're trying to get some shell code into memory and execute it, you don't have to worry about your shell code staying in memory for too long, because it will happen almost instantly. So OLLVM is by far my favorite ally against malware analysts. This, however, is not defender proof. For example, as you saw, the string hello world was still in its atomic form, right? It was not broken up. So if Yara or Defender is looking for particular strings or hex sequences of something that's not functional code, then this might not be your best bet, right? You might have to change some source code nonetheless. Now, how this is relevant to custom loaders, how OLLVM is relevant to custom loaders is that they might not get caught, right? We're still not at this will not get caught, but we went from this will get caught to this might not get caught. For example, the cloud delivered protection also asked me if I want to send it for review, and I'm pretty sure if I sent it for review, it was not going to come back with a clean sheet. So Defender did have its suspicions, but it was not suspicious enough. So the idea is to move from will get caught to might get caught to eventually will not get caught. So we're there one step of the way, one step at a time. And it naturally also depends how good of a custom loader you're writing, right? Because if you're trying to do simple process injection, OLLVM will not be able to save you, right? However, if your malware in a real world scenario, you've dropped some malware or a loader on the client infrastructure, right? You don't want that to end up in a virus total database, right? You don't want that. It might actually end up there, but you don't want every malware analyst to write Yara rules for it, because the more number of Yara rules exist for it, the easier it will get caught by somebody or the other, right? So even if it gets sent to a malware analyst, the idea is to make the job much more difficult for them to identify what your loader does. So let's just take an example of a decent shellcode loader which still fares well against cloud delivered protection and real-time protection, but it's still not the best bet against the EDRs. The EDRs let this exist on disk, right? This passes the static detection on disk, but on execution, the EDRs figure out what kind of shenanigans we're doing. So that is a particular sequence that we're doing, right? And if you're wondering what a callback function is, I guess this is visible. The flow goes like this, okay? Like here. I think these lines are not that visible, but the flow goes like this, like a snake, right? So what a callback function is essentially is it's a function that you pass on to another function, and you let this other function use the function that you've passed it to. For example, to simplify things, let's say there is an alarm function, right? So you create a sequence where the alarm has to be called, but you want the user to decide what happens when the alarm gets called, right? I'm talking from a developer perspective. So you create different functions. Let's create a beeping function. Let's create a messaging function. So you let the user decide what kind of function they want to pass on to the alarm. The alarm routine runs as it has to. All that is different is whenever the alarm gets triggered, it's either beeped or it sends a SMS based on whatever the user has chosen. So the callback function basically makes things more modular. And Windows also has that in a lot of its Win32 API. So we can actually do that. And why we do that instead of calling our function by ourselves? Because when you do something like process injection, that then a lot of APIs that are marked malicious, like create thread, etc., they get blacklisted because every malware author who has to do process injection will use it. However, there are a lot of other functions like enum windows, which what it does is it enumerates what windows you have open on your desktop. But it has a callback function which is supposed to help people who are developing software for Windows essentially count the number of windows or rearrange it, or change its own size based on um, other folders and files that are open, right? So you pass that through OLLVM, you create that decent shellcode loader, pass that through OLLVM, and now you create a malware.exe. Now, since this is custom code that you've written yourself, then there's a very less chance that it has any sort of a signature anywhere, right? So there's a very less chance that anybody has a Yara rule written which actually catches this, because this is your own creation, right? There would be functions that you use, ways that you write code, ways that you write bad code, because you might not be the best programmer out there, and hence it would not collapse into the same instruction bytes. Moreover, we are using OLLVM, which is naturally going to get rid of those. And just an image showing you that it works is here, right? We're fetching the shellcode and the key that has been used to encrypt it. We decrypt it in memory, destroy the variables, put it into a memory space, make that memory space executable in nature, and then we just call it using a callback function. And here it will not even ask us to send this to review unless you run this like 3 times a week or 3 times a day. Then Windows does get suspicious that this program is not really doing anything except for network communication. That too encrypted, that too without any headers. It doesn't seem like it seems suspicious. That's what Defender thinks like. And if by chance a malware analyst gets hands on it, do you see that? This is no longer just lines. It's a block. I can't tell where the code flow is coming from, right? It's just coming in there and just going away. And the guy who said zoom kar do, I know that's how it works. This is just for the demo, okay? Yeah, you can't tell. That's the point, and it becomes very difficult to sit down and even try to figure out. For example, the assembly that I showed you for simple hello world was easy enough for you to throw into ChatGPT and ask, what does this do? Iska kya karoge? Can't do anything with it. You can't copy every basic block and then write down which basic block is connected to which one and throw that into ChatGPT. You can't do that. Now let's move to the disclaimer. Evading defenses, specifically EDRs, is not as simple as changing few lines in the source code, right? So what we did right now is not really evading EDRs, but it's a very good step ahead, because now we're using compilers which actually help us instead of supposedly holding us back. To keep relevant in this space, you need a lot of perseverance and research skills. For example, I found out about that volatile thing, right? That particular keyword. I could have gone the other way by just writing, an unoptimizably bad set of functions and making those function calls right there. But so to keep relevant into the space, you have to be on top of every new way that a malware author is writing their own malware. And that might lead you to reading a lot of assembly code that kind of looks like this, but sometimes you just have to do what you have to do. Windows Defender gets better and better very quick, right? For example, when I was originally creating the material for it, I don't know if I would have the timestamp for the same, but it's it's July, right? When I'm testing all this out, the timestamp says July. Till September, this is not completely blocked, but we're getting that send for review pop-up, right? So Windows Defender is actually improving on a, on a very in a very fast speed, and cloud delivered protection improves at an even faster pace because they have a very good threat intel feed. And EDRs can totally eat up the loaders that you write, the custom loaders that you write, which are simple in nature. The one that I described was not the most simple, but it was still pretty simple compared to amazing samples that are out there. And the toolset that you created, meticulously removing all sorts of indicators from it, can get caught up very quickly, especially if you're using a framework like any C2, right? Because essentially there are a few parts of their code that you can't mess around with because you've not written it, and it might get very difficult to spot that one line of code in the decompiled code in the source code. For example, we got a bit lucky this time that the caret symbol was there only so many times, and that too, the one where we actually had to make a change was so obvious, but it's not always the case. And if you submit your loader to VirusTotal, yeah, you can consider it burnt, and you can consider that every vendor out there knows that you have a shiny new toy that you want to play with, and they will see you coming, right? So God forbid you do that. So that's pretty much it for the demonstration and the presentation.